We talked briefly about CPU scheduling in the introductory lesson on processes and process management. We said that the CPU scheduler decides how and when processes access the shared CPUs in the system. In this lesson, we'll use the term task to interchangeably mean either processes or threads, since the same kinds of mechanisms are valid in all contexts. The scheduler concerns the scheduling of both user-level processes or threads, as well as the kernel-level threads. Recall this figure that we used when we talked originally about processes and process scheduling. The responsibility of the CPU scheduler is to choose one of the tasks in the ready queue, a process or a thread. We said we'll just use the term task to refer to both, and then to schedule that particular task onto the CPU. Threads may become ready, so they may enter the ready queue after an I/O operation they have been waiting on has completed, or after they have been woken up from a wait on an interrupt, for instance. A thread will enter the ready queue when it's created, so when somebody has forked a new thread. And also a thread that maybe was interrupted while executing on the CPU because the CPU has to be shared with other threads. That thread, it was ready, it was executing on the CPU, so after it has been interrupted, it continues to be ready, so it will immediately go into the ready queue. So to schedule something, the scheduler will have to look at all of the tasks in the ready queue and decide which is the one that it will dispatch to run on the CPU. Whenever the CPU becomes idle, we have to run the scheduler. For instance, if a thread that was executing on the CPU makes an I/O request and now it has to wait in the I/O queue for that particular device, the CPU is idle. What happens at that moment? We run the OS scheduler. The goal is to pick another task to run on the CPU as soon as possible and not to keep the CPU idle for too long. Whenever a new task becomes ready, so a task that was waiting on an I/O operation or was waiting on an interrupt or some kind of signal, or whenever a brand new task was created for the first time, for all of these reasons, again, we need to run the scheduler. The goal is to check whether any of these tasks are of higher importance and therefore should interrupt the task that's currently executing on the CPU. A common way how schedulers share the CPU is to give each of the tasks in the system some amount of time on the CPU. So when a time slice expires, when a running thread has used up its time on the CPU, then that's another time when we need to run the scheduler so as to pick the next task to be scheduled on the CPU. Once the scheduler selects a thread to be scheduled, the thread is then dispatched onto the CPU. What really happens is we perform a context switch to enter the context of the newly selected thread, and then we have to enter user mode and set the program counter appropriately to point to the next instruction that needs to be executed from the newly selected thread. And then we're ready to go. The new thread starts executing on the CPU. So in summary, the objective of the OS scheduler is to choose the next task to run from the queue of ready tasks in the system. The first question that comes to mind is which task should be selected? How do we know this? The answer to that will depend on the scheduling policy or the scheduling algorithm that is executed by the OS scheduler. We will discuss several such algorithms next. Another immediate question is, how does the scheduler accomplish this? How does it perform whatever algorithm it needs to execute? The details of the implementation of the scheduler will very much depend on the run queue, on the data structure that we use to implement this ready queue. That's called the run queue. The design of the run queue and the scheduling algorithm are tightly coupled. We will see that certain scheduling algorithms, they demand a different type of run queue, a different data structure, and also that the design of the run queue, it may limit in certain ways what kinds of scheduling algorithms we can support efficiently. So the rest of the lecture will focus on reviewing different scheduling algorithms and run queue data structures.